Have you ever really thought about what's happening when a car speeds by, or even when you just roll a ball across the floor? It seems simple, right? Well, today, we're going to pull back the curtain on the physics of motion. And the best part, we're not just going to talk theory. We're going to take everything we learn and build our very own speed trap for a toy car. So yeah, let's get into it.
Okay, first up, take a good look at this picture. Seems pretty peaceful, right? We've got some folks in a canoe, someone on the shore, a little buoy bobbing in the water. But this simple scene is actually hiding a huge question, one that totally changes how you think about movement.
So, here it is. Who's actually moving? I mean, really moving. Are the people in the canoe moving, or is the person on the shore the one who's standing still? The answer? Well, it's not as simple as you think. It completely depends on your point of view. And, physics has a word for that.
To even start to answer that question, we have to get our heads around one of the biggest ideas in physics. Pretty much everything is relative. It's all about what you decide to measure against. And that brings us to a really, really important concept.
And that concept is called a frame of reference. Think of it like your anchor point in the universe. You get to choose it. So if you pick the shore as your fixed frame of reference, then yeah, the canoe is definitely moving. But what if you were sitting in the canoe? You could just as easily say the canoe is your frame of reference and suddenly the shore is the thing that's moving past you. See? Motion is always relative to whatever frame you choose.
Okay, so motion is relative. Got it. But now we need to be able to actually describe it. Physicists need a really precise language to talk about how things get from point A to point B without any confusion.
So let's get our vocabulary straight. The actual path an object takes, like a winding road, that's its trajectory. Its position is just, where it is at any single moment. Now here's where it gets interesting. The distance traveled is the full length of that winding road, but the displacement? That's just the straight line from the start to the finish. They can be two totally different numbers.
And that brings us to the big one, velocity. It's basically just how fast something is going. And the formula is probably one you've seen before. Velocity is just the distance you've traveled divided by the time it took. It seems so simple, but this little equation, this is the absolute key to the whole project we're building later, so hang on to it.
Now, in a perfect world, which physics sometimes likes to pretend we're in, things might just move at a perfectly steady speed in a perfectly straight line. When that happens, it gets a fancy name, uniform rectilinear motion, or MRU for short. Just picture a car on cruise control on a dead straight highway. That's MRU.
And we can see this super clearly with graphs. On the left, if you plot position versus time, you get this nice, straight, sloped line. It just means you're covering the same amount of ground in every second that passes. And the graph on the right, velocity versus time, well, that's even easier. It's just a flat, boring, horizontal line because the velocity isn't changing one bit.
But, life isn't a perfectly straight highway. In the real world, things are always speeding up and slowing down. Anytime an object's velocity changes, whether it's getting faster, slower, or even just changing direction, we call that acceleration. And yeah, there's a formula for that too. You take the final velocity, subtract the initial velocity, and divide it all by how much time passed.
So what does acceleration look like on one of those velocity time graphs? Well, check it out. The graph on the left, where the line is sloping up, that's positive acceleration. Our car is speeding up. And on the right, see how the line slopes down? That's negative acceleration. In other words, the car is hitting the brakes.
So we know how to describe motion, but we haven't talked about why motion changes. Why do things speed up or slow down in the first place? Well, the answer is forces. And the guy who wrote the rule book for all of this was, of course, Isaac Newton.
This little flowchart pretty much sums it all up. Look, if there's no overall or net force acting on something, it just keeps doing what it's doing. It either stays put or it keeps moving at a constant velocity. Hey, there's our old friend MRU. But the second you add a net force, bam, you get acceleration. You speed up, slow down, or turn. That's it.
And it all comes down to these three legendary laws. First up, inertia. Basically, stuff is lazy. An object is going to keep doing whatever it's doing unless you push it or pull it. Second, the famous F equals m times a. It just means you need to push a heavy thing way harder than a light thing to get it to speed up. And third, action-reaction. For every push, there's a pushback. Simple as that.
Okay, that was a super fast tour of the physics of motion. But, theory is one thing. It's time to get our hands dirty and see how all these ideas actually work in the real world with a fun little project. So let's just do a quick recap of our toolkit. We've got velocity and acceleration to describe motion, And we've got forces and Newton's laws to explain why motion changes. We have the language, and we have the rules of the game.
Which brings us to the big question. That's all great, but how can we actually use this stuff? How do we take that neat little formula for velocity and turn it into something we can actually measure ourselves? Well, we are going to do exactly that. We're going to build our own speed trap, a device that can measure the velocity of a toy car. And the brain of this whole operation is going to be this awesome little programmable computer called a microbit.
All right, this is the best part. Let's get into our final section and actually build this thing. We're going to make a set of simple timing gates and use our microbit to do the math for us, putting all that physics theory into practice.
And don't worry, you don't need some fancy physics lab. All you really need is some stuff you probably have lying around the house. Cardboard, aluminum foil, some tape, a few clips, and of course, our microbit and a toy car to race.
Building it is actually super simple. We're just making 2 gates on a piece of cardboard. A gate is literally just 2 strips of aluminum foil, placed really close together but not quite touching. Then we hook up each gate to the microbit with some clips. And last, we stick a little strip of foil on the bottom of our toy car.
So, here's the magic. When the foil on the car rolls over the first gate, it touches both strips at the same time and completes an electrical circuit. The microbit sees this immediately and saves the exact time. We'll call that time T0. Then, when the car hits the second gate, the same thing happens, and the microbit snags that new time, T1.
And now we bring it all home. We've got our start time, T0, and our end time, T1. If you subtract them, you get the precise time it took for the car to travel between the gates. All that's left is to grab a ruler and measure the distance between those 2 foil gates. And then we use that exact same formula from way back at the beginning. Velocity equals distance divided by time. And just like that, you've built a real-world speed trap.
So think about that. We went all the way from these big, abstract ideas like frames of reference and Newton's laws, right down to building a working device with cardboard and a tiny computer. It's just a perfect example of how the language of physics lets us actually understand and build things in the world around us. So, we measured a toy car, but you could use this for almost anything. What would you measure next?